Thanks for having me. Thanks for coming. So I'm here coming, from a small nation of 2 million people under the Alps, and I'm here to tell you about my research. So what I want to do for this is I want to do both kind of the overview and the introduction for the entire session and kind of the speakers that are coming, motivate some of the things, and then give you a few vignettes, kind of short themes about the research happening in my research group at Stanford. And really, if we think about, I think Steve said it nicely, we think about social networks, but really I think we should be thinking about how do we model human data and how do we model humans. And now is the right time to start thinking about that because we as society, we as humans, we are generating like a big digital footprint and everything. We do that about ourselves as individuals. We do that about how we interact with each other. We do that through the places where we live and where we go. And we also do that in terms of our physical environment and so on, right? So it's really, the idea is that basically everything we do in our personal life as well as in our organizations gets captured and kind of generates digital traces that can be analyzed in order to do something better. So there are kind of two questions we want to do when we say we have these digital traces of user or of human activity. The first thing is kind of, it's a scientific question, which is about, can we recognize fundamental patterns of human behavior? So it's almost like, can we write down physics equations of human behavior, right? Can we take digital traces as a telescope into humans, into society, to understand how we operate, how we behave, what makes organizations successful, what makes businesses go up, what makes businesses go down. So that's the first question, is this notion of can this type of data give us a window into fundamental behaviors? The second thing is kind of, it's an engineering question, is how do I use this data to design in this space, to basically make new, better applications? So I can start thinking about what kind of new products, different types of decisions can I do based on the analytics knowledge coming from this data. And I can think everything from things from being able to predict things, being able to make recommendations to my customers, users, recommendations about what should I do next, think about forecasting, what is going to happen, and also think about diagnosis, right? How can I go and analyze the past to learn from it in a human interpretable way? So these are kind of different aspects for the second question, which is about how do I act, how do I build, how do I design in this space? And there are two, I think, things that are very important if we say we want to model humans and how we behave. So the first thing is that we interact, right? We are not this kind of IID, isolated data points independent of each other, but we operate in networks. We interact with each other. And by these interactions, we actually influence each other. And this becomes very important signal in a sense that, my state depends on the states of my neighbors. And this way I can start sharing data and learning much more about every individual. And then the second important thing is the notion of content, right? Is that we communicate with each other. We talk, we exchange text. So understanding the messages that we exchange is also very important. So my research group at Stanford combines the analysis of large-scale data, large-scale networks with big data analytics to build computational models of behavior. And kind of our theme has been that we really want to work with large-scale data to see, observe, understand patterns that otherwise are invisible if you work with small data. And then with this, we had applications to computational social science, kind of basic scientific contributions, as well as a bunch of new methods that get applied to companies like Pinterest and Facebook and LinkedIn and others. And what I want to do today is tell you about, kind of take my title and explain it in 4 different examples. So first in my title was humans. So I want to give you an example of a research project we are working on where we use machine learning to help humans make better decisions. Then the second part of my title was content. So I want to talk about social media analytics and modeling information flows. And I'll tell you what I mean by that. And then I'll talk about places, which is how does physical environment influence us as humans. And then at the end, hopefully I'll have time, I'll talk about some kind of fundamental data mining machine learning algorithms that enable the research on the top. Okay? So first I want to talk about this notion of how can I use machine learning to do better decision making. And the idea, really, the questions here will be, can machines make better decisions than humans? Why do humans make mistakes? And can I use machines to help humans make better decisions, to diagnose the decisions we are making? And when I say decisions, this is really what I mean. I mean that we make these decisions all the time, right? So we make small decisions like what should I eat for breakfast, all the way to, in medicine, how do I treat a patient? In education, will this student drop out and I have to do some intervention? Or in criminal justice, where the judge is being asked, will this person commit another crime if I leave them out on bail? And these are all essentially prediction problems about what will happen if I do X, right? And today, humans make these decisions. But it's really time to start applying data science and machine learning techniques to try to help making these decisions better, okay? So now if you think about human versus machine, right? There is this information asymmetry and advantage where humans many times see more information than the machine does, and they can also see this kind of soft personal type things that are very hard for the machine to quantify. But on the other hand, humans are biased in decision making, both many times subconsciously, sometimes also intentionally biased, right? And the question is, how can we build machine learning tools to gain insights into these types of behavior? And what we did, among other things, is we built a statistical model that allows us to look at judges making decisions on items. Items can be other humans, but these are items on which we are making decisions. And the idea is that we want to find sets of judges that are making decisions in a similar way on a given subset of items. So it's like a double clustering problem where the goal is to infer these confusion matrices that say how true labels or true decisions, the correct decisions, relate to assigned or decisions made by the human. And through this, we take this framework and we applied it to a couple of decision problems. So here's one that's kind of very important for the society. Around 12 million people get arrested in the United States every year, and the question is, where do these people wait for the trial? They can wait being free, or they can wait in jail. So the judge, the human judge, every day has to decide, should I take this person and let them be free until their trial, or should I should I leave them out on bail, or should I keep them in prison? And the question is, if I leave this person out, will they misbehave? There are two types of misbehavior. One is the person is going to commit another crime, and the other one is they will flee the country. They won't show up at the court for the trial, right? And we work with more than 1 million criminal court cases where we actually have these human decisions. And then, for example, the question is, how could machines help now criminal courts do better decisions? It turns out that algorithms do around 60% better. So this means we could have 60% less people in prison while keeping the crime rate the same. So we could increase the release rate. Or the other way, we could say we will keep the same prison population, but we could decrease the crime rate by a lot.
Is it the baseline 50%, yes or no?
No, baseline, judges tend to release, I think, around 70% of the people, and their crime rate is around 20%. Right, so out of the people who get released, around 20%, things go bad. Random decision is a disaster. Right, baseline is not random. Baseline is what human can do. And humans today release around 70 to 80% and have around 20% error rate. So out of the people who get released, 20% commit another crime. We can drop that to 8, okay? And the other thing that is important is not only that we say machines can do better, but you can actually come back and say, why are judges making mistakes? And it turns out, I won't tell you how to figure this out, but you can figure out that they are putting too much weight on subjective information. So basically, defendant's demeanor. While algorithm only has access to the criminal record of the defendant, the judge also sees the person, and we can show that what they see makes them do wrong decisions. The way we see that is that we can train a machine learning model that predicts what tries to imitate the judge, predicts what the judge will do, and that model is better than the judge himself. So a model that tries to imitate the judge makes better decision than the judge, okay? And then you can gain other insights. So that's the first place, right? But you can do this type of things and apply it to many other domains. One domain where you could do this is where humans give you labels, like crowdsourcing. And you can start asking, are my workers biased? And what groups of my workers are performing particularly well? And what groups are not performing well? So one thing is, for example, you can have a document labeling task where you ask people to distinguish between atheism, Christianity, baseball, and hockey topics. And for example, you can learn that the idea is red colors mean on the diagonal means you're making correct decisions because whatever should belong to a given category you put in a given category. Here you, for example, learn that in this task, kind of stereotypically, female evaluators would give themselves a low self-reported confidence score, but they are doing super precise decisions. You find out that male evaluators that are lower than 3 years and judge short documents don't know how to distinguish between Christianity and atheism. They know how to distinguish between baseball and hockey really well, but here it's random. Okay? So things like that, right? Great. So why is this important? This was my first thing. This is important because it helps humans make better decisions. It provides insights into the decision making and kind of goes to this idea that we really need to get machines and humans work together. And really, I think this is extremely important if we start thinking about applying machine learning to high stakes prediction problems, right? Like things that are more serious than showing an ad or recommending a movie, right? Then you want this cooperation, collaboration between the human and the machine, and you want to make the best possible decision. Yes? I know that work briefly. So the question was about fairness of algorithms. Yeah? Moving. Completely correct. There are a gazillion of ways how to do this wrong. We did it the right way. I don't know what else to say. Yeah, you have to be very careful about how you train. You are a very strong technical guy, but for the rest of the mere mortals like us to make the right decisions, I wanted to know if there's a better training since you're getting into human decision making and making. Yeah, I mean, it's extremely important how you train these models. It's extremely, for example, important in this bail example that you also, that you are making decisions about future, not that you are not just doing cross-validation, but you're really saying I'll use last 5 years to train and then I'll predict what happens in the next 5 years because distributions change. The other thing that is important, for example, you cannot take one county and release everyone there and then another county lock everyone down. So you also want to respect kind of try to release across. So there is a bunch of questions that come that you need to figure out when you deploy this. Another thing, for example, that turns out to be very important that kind of in machine learning, people tend to ignore this and in medicine happens a lot, is that you only observe the label after you treat. So I only see the label of the people I release. Everyone I put in jail, I never see their label. I cannot know whether they would truly commit a crime or not. So the question is, how do you deal with that? We have ways to deal with that. Happy to talk more later. Great questions. Okay, good. Moving on, I'm very slow. So about the other thing that we do a lot is understanding content. So in terms of social media analytics. And the point here is the following, right? Is the traditional picture was something like this, right? There was the mainstream media and then the information kind of propagated from mainstream media through the society. Today, the way we consume information has fundamentally changed. We get information in real time, in small bits conveyed through networks, right? So really what we can start thinking about is how does information and behaviors spread through these networks, right? How does kind of behavior go from one node to another and spreads like an epidemic? And you can think about many types of epidemics. So for example, one epidemic we've been analyzing is the epidemic of LinkedIn, right? So this was an epidemic that started in Mountain View and in around 10 years affected 332 million people. And between 60 to 90% of these people got infected because somebody invited them directly. So this is now a product adoption cascade where you say, how do I make my product spread virally and people kind of start adopting my product? And here's just one example of how usage of LinkedIn spread, right? Each person here, you know, they invited a number of people, then some of these invited another set of people, and so on and so forth, and you get this kind of cascade. So for example, we see this cascade that in 3 days goes through entire Denmark, and afterwards 15% of the people, of the population of Denmark is a member of LinkedIn, right? So we can study these types of processes, which is product adoption. Another types of things we can do is around brand analytics, where you can go to the kind of the online chatter, everything from mainstream media all the way to blogs and Twitter and so on, and start asking what is the brand sentiment. And we did a case study with Boeing around the time they had the problem with the Dreamliner and the battery, and the thing was catching fire and things like that. And you can start asking, you know, how does the media react? You can actually start doing sentiment analysis and trying to understand what are the phrases around which people agree versus what are the phrases that are kind of the most controversial, that take people apart. And this is kind of a consensual phrase around this time when there was a battery problem about, and this is the one that was kind of the most controversial, and you can kind of intuitively see the differences. And then the last thing I can say is, you know, one is modeling product adoptions, doing brand analytics, but also thinking about predicting how information is going to spread through networks. And this was one of the collaborations we have with Facebook, where we are trying to say how much will something spread throughout the network. So the question is, can you predict what will go viral, if you like? So you see the first few reshares of a piece of content, and you want to say, you know, how big will the thing be eventually? And here we've been working with Facebook, with complete Facebook data, hundreds of millions of photos or billions of photos. And you can start asking what characteristics are predictable for this, that would tell me whether these information cascades are predictable, right? One is what is the content that is spreading. The other one is who are the people that are trying to spread it. How does the network structure look like, where the entire thing is spreading, and also how has it been spreading so far, right? Just like kind of temporal characteristics. And I should just say for the context, actually scientists have been thinking or saying that these types of processes are inherently unpredictable because there is so many different factors and it's very hard to guess what is going to happen. What we actually show, if you have enough data, you can do these predictions quite well. So you can do them with around 80% accuracy. And it turns out that kind of the most important factor is, you know, just the first few propagations that you see, those tells you a lot how much the thing is going to spread in the future. Early on, it's also very important who the user is. Content, maybe we were not able to capture it good enough, but that was not very predictive whether something will spread or go viral in a network. So this is kind of my second point, which is, you know, what can we do with social networks? We can analyze how information, behavior, products spread through these things. And this is particularly important because today we live in online networks. We consume information through online networks in real time in small pieces, right? And this allows us to do consumer brand analytics, marketing communications, product adoption, product sentiment. So that's kind of the second theme of work. Moving forward, third theme of work. About places. Here, I want to show one example of what we are doing with data science for understanding human physical activity. And in particular, we are working with devices that most of you are wearing on your hands, but kind of don't know why, I guess, right? The reason is we wear these physical activity tracking devices, and the question is, what do these devices tell us about how we are physically active as humanity? And then also to an individual, how can these devices make my life better? So we are working with one of the Silicon Valley startups that has a particular device. It's an iPhone app, so it measures your physical activity by having a phone in your pocket. Around 2 million people, 74 million days of activity tracking, and more than 100 billion data points. And if you look at this data set, the first question is, how representative is this of general US population? And you find out everything is very, very close what, you know, medical research on sample between 10 and 100 people has figured out. So you have the right proportion of males to females, the median age is kind of right, the fraction of obese people is about right, so it kind of matches what we know about the population. But now, of course, with this data, you can go much deeper. So for example, one thing you can start looking is how does the distribution of activity change across the countries, and how does it change across the different genders? And what we find out is that the way the activity is spread or distributed in the population changes a lot. So for example, we define this notion of activity inequality, where, for example, in Japan, men and women are about equally active. And if you look, for example, in Saudi Arabia, that is a very unequal in terms of activity country, you see how, male activity, yes, compared to, let's say, United Kingdom, drops a bit, but the female activity drops even more. And we see these kinds of patterns where this activity inequality is extremely predictive of various types of properties of the country. So for example, here is one, where is different countries, activity inequality and fraction of obese people. And this is actually a better predictor of how many people in a country are obese or what fraction than just say, oh, how active are people. It's really about what fraction of the population is activity poor, and how is this activity distributed or spread inside the population. So now, how does this connect to the environment where we live in? So for example, in United States and across the world, for every city, we compute the walkability score, which is, how many things can I walk to? And you can start asking, does the walkability score relate to the obesity and physical activity? And this is what I'll show you next. This is now, here is only US data. This is the walkability score. Here on the right, it's New York, Boston, San Francisco. And there on the left is like Austin, Texas, Dallas, Fort Worth, things like that in Texas. And you see this super strong correlation between walkability and activity inequality, right? The activity is much more unevenly distributed in low walkability cities and much more evenly distributed in high walkability cities. You can look, for example, with different cities. This is now time of the day over a weekday, time of the day over the weekend. The y-axis is physical activity. This is average number of steps in a 30-minute interval for high walkability cities in green and low walkability in blue. What you see that in high walkability, people are active in the morning, kind of going to work, around lunchtime, and in the evening. In low walkability cities, you see much less of that. Interestingly, you see the same things over the weekends as well, that over the weekend in high walkability cities, people tend to be more active. And maybe what is the bottom line here is that it turns out that females are much more sensitive to the environment. So the price that a female pays by 1 point change in the walkability score is higher than what a male pays, right? But just kind of this shows this connection between physical activity and the environments in which we live at. So what are we doing now with this, right? We're really thinking about how do we influence or how do we help people to live healthier or better lives. In particular, what is the role of social networks as in terms of like support communities? How can we create challenges or competitions that change behavior and make people more active? And also, how do we nudge humans in appropriate directions, and this way provide value and take these devices that we are all using to actually help us live better lives, okay? So these are the three themes of kind of research science I wanted to talk about. I want to finish with some kind of more technical things my group has been doing about analyzing networks and graphs. And I'll just show two examples. So the first one is really to think about how do we join networks and convex optimization methods. And the idea is basically, can we come up with these large-scale optimization solvers for problems that can be represented as graphs, as networks, where we think of every node of the optimization problem as a small sub-problem, and edges tell us how these sub-problems are coupled with each other. And you could think about this, in cyber physical space, in social networks, financial transaction networks, things like that. And just graphically, the way to think about this is that every node in this network has its own objective function or its own optimization problem, and there is some kind of coupling between the nodes, some kind of dependence that is captured by the edges of the network. And what I would like to do is, I'd like to solve this by finding the global solution for every node in the network. And kind of the bottom line is that we can do this really, really well and kind of orders of magnitude better than what existing methods can do. So for example, we can solve for 100 million unknowns in around 14 minutes on a single machine. And where we are taking these methods and applying them is we are applying them to the IoT domain. And I'll just give you an example, what are we trying to do there. So the idea is we have lots of this sensor data, time series data that we try to understand and analyze. And the idea is that you can think of these sensors as different time series giving you different types of measurements. And what we would like to do is we'd like to understand how are these sensors related to each other as time goes on. So we would like to infer these types of networks that tell us how are these sensors correlated with each other. And right now we are applying this to big machines like planes and so on, where you want to understand what is happening with the plane from, taxiing, taking off, and landing. How do these different sensors relate to each other? The other thing you want to do is you want to do error diagnosis, right? When something goes wrong, how do you when a sensor starts behaving weirdly, how do you figure out what is the cause for that weird behavior? Some kind of root cause analysis, it's called. So this is one. And then the last one I want to talk about is applying machine learning to networks, where kind of always the problem is that we start with raw data, we create structured data, we build a learning algorithm, and then we apply it to some model. And there's always this step of doing lots of work to find the right features, compute them, and do the feature engineering. So what we are trying to do is we want to get rid of feature engineering and automatically learn the features. And just with quick, what do we have? We have an efficient task-independent feature learning algorithm for machine learning in networks. The method we call is node-to-vec because we are able to learn how to transform every node into a feature vector of maybe 50 dimensions or so. And this way, we can then use these feature vectors to do machine learning in networks. And I'll just say a few things. First, these methods we have scales to networks of millions of nodes. If we want to do node classification, we get state-of-the-art performance, up to 20% improvement in accuracy. And also, we can learn different types of features. And what I'm showing you here is the same network twice, where I color nodes that have similar features. I color them using the same color. And what you see here is, for example, we can learn this notion of bridge nodes, periphery nodes, and this kind of nodes that are well connected, right? So red are the nodes that have good number of connections, blue are the kind of the bridge nodes, and then the yellow nodes are the periphery nodes with low number of connections. These are types of things we can learn, or we can learn this kind of clustering of the network where you see kind of nodes in the same region have the same types of features. And we have a flexible way to kind of interpolate and learn the right features for your classification problem. Okay? So with this, I will be done. Really kind of on the big picture, stepping back, my talk was about the fact that humans, society, we are generating lots of data, lots of digital traces, and data science can help us understand and predict human behaviors. And these are consequences for how do we make better decisions, how do we understand kind of the opinion of the crowd, of the society towards a brand, towards a product, how do we make the product be adopted throughout the ecosystem, and also, how do we design new and more personalized products applications. So with this, I'm done. Maybe I have some time for questions, or I'm also be done.
Sure.
All right, thank you.
We do have a microphone.
Sure. You had a slide showing the temporal pattern ranked the first most accurate model. Mm-hmm. So I wonder, for temporal pattern, I'm understanding we have you're not only interested about the sequence, you're also interested about the interval of adjacent events, right?
Exactly.
So what's your view of, because my experience is it's kind of a quiet topic, not many interests about to find temporal pattern algorithm to in a simplified way or unsimplified way. Have you done something similar to that to, for example, characterize the digital footprints of the customer, detect the lifetime events of the customer, and then optimize that to find the most important temporary pattern for recommendation or product recommendation?
Yeah, we do that a lot, and especially that becomes very important if you want to model how the intent of a customer to act builds up. So understanding the kind of the temporal sequence of events and how actions are following one another becomes very, very important to know how is this kind of building up to the conversion or to some final.
So you still formulate the problem as a network way, or you consider it's a
Then we more think of it as a times, depends on how do you want to think about it. Do you want to think about it as a set of interactions with others? Then you think about a network. Another way you can think about a network, you can think of it as a linear network, a linear sequence of time steps, and thinking about how this goes.
Okay, so by your experience, which one is more efficient? Because I think you mentioned about network, large-scale network. I feel you think network is more efficient when you have large data, huge data scale, then you can scale it up easily rather than the linear search or something.
That's true. I mean, we can go into questions: how are we computing on top of these networks? But I think the right representation depends a bit on what exactly is the data and what exactly is the question. So happy to talk offline.
I had a question about, have you applied this to how organizations work inside, how organization works with other organizations? Many times there are joint development programs, how organizations work with universities. I mean, the characteristics of that working relationships and its impact on the performance.
Great question. So the question, I guess everyone heard, yes. So we are actually doing that. I didn't talk about, but one project we have is we have all the data about Stanford University for the last 26 years, about productivity, people getting tenured, co-advising students moving around, and Stanford is a huge organization, so that's one place. We also are working with HR data to understand human employee performance with the goal, how do we create good working teams? So it's kind of team composition, how do you understand that? Chris Potts in the next talk will actually talk about how can you understand the communication patterns and language people are using to predict how long are they going to stay in a company, right? That's one example. Actually, we started that research to do it for online communities, where the question was, will a person remain a contributor in an online community? It turns out that those same methods can be generalized to say, will a person be active in a company? So definitely. I think there is a huge benefit and a huge opportunity. What has been a bit hard, it's been a bit hard to get the data. So either we would find online counterparts. Another example is Wikipedia, which you can think of it as an organization that is producing articles, things like that. But good question.
Thank you very much, Jure.
Okay,
Why don't we
thank you.
go on to the next speaker?